Our next task is to define the algebraic boundary operator for singular chains. So let's consider a basic example like this. So we've got this. We'll just do this in the plane R2, and we've got some points A0, A1, A2, and they give us a linear two-simplex. So this is pointy brackets A0, A1, A2, and let's recall exactly what this means. This means that U is a map from the standard two-simplex delta 2 into the plane, and it's defined by U of T0, T1, T2 is T0, A0 plus T1, A1 plus T2, A2. Okay, that gives you this triangular picture here. So what's du? Is the boundary of U. Okay, so that's what we need to define. But you know, the kind of obvious sort of thing that it should be. I mean, it should consist of the three edges of this triangle. Okay. Okay. So what are these three edges? So obviously there's an edge here from A1 to A2. So that's going to be one of them. And then there's also an edge for A1 to A2 and an edge from A0 to A1. Okay, so the next term here, we're going to, that was A1, A2, and then we're going to do A0, A2 here. But I'm going to put in a minus sign here. So I'll explain that minus sign in a second. But so here, A1, A2 is this edge, and then we've got that edge, and then we've also got this edge here from A0 to A1. Okay. Okay, so what's this about? I mean, we want a kind of formal definition that sort of just captures the idea of just going around the edge of this triangle. But we want it, as we discussed in a kind of informal discussion of homology earlier, we want d squared to be zero, the boundary to be zero. We want this du to kind of correspond to sort of just running in a sort of circular fashion around the boundary, and so that we've got no edge left. But to go in a circular fashion around the boundary, you want to go from A0 to A1, and then from A1 to A2, and then backwards from A2 to A0. And it's kind of because, but for other purposes, it's kind of convenient for bookkeeping if everything always stays in the same order, in sort of ascending order of indices. So we don't want to say A2, A0, because that would mess the indices up. They go the wrong way around. But instead, to sort of correspond to the fact that we're supposed to be carrying around anti-clockwise in the same way, we've just put in this minus sign. Okay, we'll see a bit later a more systematic way to deal with this issue with plus and minus signs. But for the moment, we'll just draw it like that. Okay, so so that's what we would define for the boundary of a linear two-simplex like this. More generally, for a linear simplex, we want to make a definition like this. We've got a linear simplex of higher dimension. So what we're going to do, I mean, so look, what did we do here? I mean, here we just left out A0, and here we left out A1, and here we left out A2, and that's the general rule. Okay, so you do the thing leaving out A0 and minus the thing where you leave out A1 and then plus the thing where you leave out A2. Okay, so that's kind of a general rule. Or maybe we'll write this in a slightly different way. Okay, so to just say that general rule again for a linear n simplex. So this is going to be an n chain in some Euclidean space R, the capital N. Du is the sum from I is 0 up to n of then we have alternating signs, so it's a -1 to the power I, and then the thing with AI omitted. Okay, and so and this, of course, it's a linear combination. You've got a sum of terms with plus or minus signs, so integer coefficients, and so this is a linear combination of simplices of one lower dimension. Okay. So that's what we're going to do for linear simplices. And we kind of want to do the same thing with nonlinear simplices. So let's just draw another picture. Okay, so here's a curvy two simplex. Let's write U here to indicate this is the image of a nonlinear map U from the two simplex into some space, which might not kind of looks like it's R2 here, but it could be any space. Okay, and it's got some vertices A0, A1, A2 again. Okay. So for a nonlinear two simplex U, so this is a map, remember, U is officially a map U from delta 2 to X. So du is, is like, well, informally at least, this is the part of U from A0, A1 to A2, minus the part of U from A0 to A2, plus part of U from A0 to A1. Okay, so we can kind of see these things, these paths here in the picture. But we need to be a little bit more precise. What exactly do we mean by the part of U from one point to another point? Okay, to explain a bit more precisely what I meant on the last screen, we need to go back to remembering the definition of the standard two simplex. Okay, so remember delta 2. That's the set of T0, T1, T2. So triples T0, T1, T2, whose sum is equal to 1. Okay. So we've got the three vertices. There's E0 here, and then 0, 1, 0, which is E1, and then 0, 0, 1, which is E2 up here. And then along here, here your third coordinate is 0, and then along here you've got kind of like T1 minus T0 along this edge. Along this edge, these are all the kind of points where the first coordinate is 0, so this is kind of 0, T, 1 minus T. And along this edge, this is where the middle coordinate is 0, so you've got T, 0, 1 minus T. So given any kind of sort of nonlinear two simplex into some space X, you have three maps from delta 1 to x, corresponding to the three edges here. You've got the one that goes t 1 minus so kind of the one that goes along here is u of 0 t 1 minus t, and then alternatively you've got the one across here. There's u of t 0 1 minus t, or so this one is u of t 1 minus t 0. Okay, so let's okay. So we could call these kind of v0, v1, v2, if you like. Okay, and so this is just the way the indexing works, right? You've got an e0 here, and then the edge opposite e0 is this one here, and then this so this v0 is kind of running along the edge opposite to e0, and this v1 here, where I got t0 1 minus t, that's this edge here. There's the one that's opposite e1, and v2 is the edge that's opposite e2, running along here, and the boundary of u is going to be this kind of v0 minus v1 plus v2. Or another way we can say it, the way that's kind of more makes it easier to sort of organize what we're saying and generalize it to higher dimensions, is like this. We define delta naught, delta 1, delta 2. These are the three maps from delta 1 to delta 2, the inclusions of these three faces that we've drawn along here. So delta naught, I mean, it's basically this map here, but we'll write in a slightly different way. T0, T1. So this is the one where you just insert a 0 at the beginning. That's what we did over here. We stuffed in a 0 there. So 0, T0, T1. And delta 1 is basically what's going on here, where we stick in a 0 in the middle. And delta 2 is where we stick in a T0, a 0 on the end. Okay. And then we can say that the algebraic boundary of u that we wrote here is well, this first one, our v0, it's just the composite of u with this delta 0. And then the second one is the composite of u with the map delta 1. And then the third one is u composed of delta 2. Okay. So that's how we get the kind of algebraic boundary of a two-simplex. And this version kind of works even if the two-simplex is nonlinear. Okay, so now here's the fully general picture. Okay. So we've got any n greater than 0 and I with I between 0 and n. We're going to define this so-called face inclusion, delta I. This is going to be a map from the n-1 simplex into the n simplex. So we have to say what's effect on some tuple t0 to tn-1 here, and then what you get is you have t0 all the way up to ti-1, and then you stick in a 0, and then you get ti all the way up to tn-1. We can kind of label the positions here, right? I mean, this is sort of position 0 all the way up to position i-1. That's in position I, this is in position I+1, and this is in position n. Okay, so we've got entries from 0 to n, and we've stuffed in a 0 in position I. Okay. Then okay. So now if I've got some map from n simplex into a topological space X, then I define du to be this this expression here. So for each I can compose my delta n with compose my u with this map delta I here. So u composed with delta I, that'll be a map from delta n minus 1 into X. And so we take a linear combination of such maps. That counts as an n minus 1 dimensional chain, like so. Okay, but yeah, so now I haven't quite, so far I've not quite done what I needed to do, right? I mean, a typical element of CNX, an n chain, a singular n chain in X, is not just a single map like this, but it's a linear combination of some things like this. In this situation, du, well, I just do what I have to do. Okay, I want my D to be a homomorphism. If it's going to be a homomorphism, it has to sort of be act linearly, like so. So each of these UIs, each UI individually, is a map from delta n into X, and so you use this rule over here to define what we mean by the boundary of UI. And for this this U, which is a linear combination of the UIs, well, you just sort of do the same linear combination to get the boundary. So that's what we mean by the boundary of this this chain U here. So this defines a homomorphism D from Cnx to Cn minus 1x. Okay, so this definition may seem quite abstract, but it's not very hard to just draw little pictures to illustrate it. So one kind of thing that we can think about is this sort of situation. We've got edges in a row like this. So we could look at we've got a chain like this: A0, A1 plus A1, A2 plus A2, A3 plus A3, A4. And what's the boundary of that? Well, so we just the rule is you omit the thing in position 0, which gives us an A1 minus what you get by omitting the thing in position 1, which is A0. So that's the boundary of this guy, which is it's like this. This refers to this edge here, and the boundary of this edge obviously consists of A1 and A0. And it's just a little bit question about how we do the sine rule. And the sine rule is that this kind of arrow is going into A1 and out of A0, so you get a plus A1 and a minus A0. And then for the boundary of this guy, it's kind of the same. You get A2 minus A1, A3 minus A2, A4 minus A3, and everything kind of cancels out mostly. And A3 there cancels that A3, that A2 cancels A2, the A1 cancels the A1. And so you just get A4 minus A0. In other words, the kind of boundary of this combined chain is just the one end minus the other end. It's kind of more or less the same as the original rule for an edge. Okay, so now let's do an example involving two simplices. And so we can have a picture like this. A, B, C, D here. And let's consider, so this is in some space X, and we're going to put, so this is some space X, which we're going to assume is in Rn, so that we can talk about linear simplices. So let's consider a chain like this, say A, B, C, minus A, D, C. Okay, so that's consists of these two triangles here. And let's look at the boundary of this. But let's just maybe discuss this kind of minus sign here. We really want to be kind of thinking of both of these things as going sort of being oriented the same way, sort of anti-clockwise like that. So ABC is anti-clockwise, and then if we wanted to sort of do this anti-clockwise, then the sort of natural thing would be to do ACD. But it turns out to be tidier if we do ADC, but then ADC would be going clockwise, so we put it on minus sign to compensate for that. But so let's just take this as our definition. U is going to be this this chain like this, and then so what's the boundary of U? Okay, so the boundary of this one, you omit the thing in position 0, leaving your BC, and then you omit the thing in position 1, but with a minus sign. And then you omit the thing in position 2 with a plus sign. And then here, you omit the thing in position 0, go to DC, and then you've got that minus sign you already had. And then you omit the thing in position 1 with an extra minus sign, cancelling that one, so you get a plus AC, and then minus AD. And we notice that the AC thing here, the thing that cuts across the middle, that comes with a minus sign here and a plus sign here, so these ones cancel. So we're left with, this way, so you've got an AB and a BC, and then you've got a minus DC, and a minus AD. Okay, so there's the boundary view. It consists of like the four edges around here, and then there's the usual business about the plus and minus signs. But now let's actually calculate the d squared of U. Okay, so the boundary of U. So we're looking at the boundary of this. So do the boundary of your AB here. That's B minus A. And then the boundary of this BC is C minus B. And then minus the boundary of this, which would be C minus D. And then minus the boundary of this, which is D minus A. Okay, so that's B minus A plus C minus B minus C plus D minus D plus A. And so this B here is cancelling that minus B there, minus A there, cancelling plus A there, plus C, cancel minus C, and the D and the minus D. So we just get 0. And in fact, d squared equals 0 always. That's a key fact that we need in order to set up homology theory, but we'll do that we'll prove that in the next video.